This video here where we'll discuss the unique kind of chemical and material science engineering aspects of how zinc is applied to copper using granular zinc, represented here, in basic media like sodium hydroxide in water. In an earlier video, we walked through a nice video where we had the experiment discussed and some animation provided in this YouTube link. And so I invite you to kind of consider watching that if you haven't. And some of the animation screenshots are shown here on this slide for us. So in that video, it's highlighted that the copper in a penny can transform into a silver appearing version of that, and ultimately with some later heat of the dry penny on a hot plate, the brassy kind of gold appearance can come through for that very same penny. The video does a good job of emphasizing just how surprising this is, given what we know about zinc and its standard reduction potential relative to copper and other species in the reaction. So they'll go on and emphasize that the second part of the reaction, quote unquote, is not straightforward, not expected. And so the idea of here generating zinc solid from zinc ion away from zinc and on the copper is what's interesting there. So we'll frame our discussion here considering the Gibbs free energy equation and the standard reduction potential values from a table, considering some options as we digest this process. So the first question we could ask is whether the zinc can just plate out onto zinc. So if there is zinc already, can zinc ions simply add to that? Okay, so to help discuss this, what we would do is turn to our standard electrode potential table here and look for the relevant species. So in our video, we see that zinc solid can kind of produce zinc ions, so that's one half cell reaction. And then we're discussing whether or not zinc ions can generate zinc solid on the coin thereafter. Okay, so what that looks like is simply scanning down the table here and looking for a relevant half cell reaction. So here we have zinc ions plus electrons forming zinc solid, and that would be the one that we would consider. So the granular zinc here would have a half cell reaction looking like this: zinc solid being oxidized to form zinc 2 plus ions in the medium. So we'll say aqueous there. Recall that the medium here is high pH hydroxide, sodium hydroxide in water. We'll touch on those implications in a moment, and then there'll be 2 electrons as a result. So in the video, those 2 electrons in the metallic copper penny are kind of highlighted here as these sort of green little features to put some attention to that. Of course, these electrons are a quantum material and kind of are distributed throughout the conductive metal as well, but a sort of a particle representation is given in the animation for us. Okay, so that is the dissolution of the granular zinc here, and we know that that has an E value at standard potentials in conditions here of 0.763 volts. So notice that's a positive value, 0.763 volts. So I had to flip the equation down here and therefore flip the sign on that from the listed one at here in the table. So we've discussed here the granular zinc piece thus far. Now the other part is taking ions that are in the medium and asking them to add to the surface of the coin. Okay, so we'll consider that taking zinc ions from solution, aqueous, and asking the electrons in the green to act as the mechanism for taking us from zinc 2 plus all the way down to zinc 0 and adding more solid to the surface of the penny. And this is now the standard reduction potential exactly as we see it here. And so that's a negative 0.763 volts. And therefore the sum of this is 0 volts. Okay, so we have no sort of standard electrode potential for the cell, no driving force in our equation here, so to provide a negative delta G outcome. So we would, from this analysis, predict that plating zinc onto zinc as the gray is developing in our coin is not a spontaneous process. So that doesn't fit with our observation, obviously. So there's more to the story, therefore. Okay, so I'll just clean some of this up so the animation can formalize that for us. Okay, so we see that these basically cancel out. All right, so the next question we can ask is, what about the copper? Is the copper involved? Perhaps the copper is being sacrificed in the penny or in the metallic structure, and we're generating a reductive process that way for taking zinc ions from solution and adding zinc to the surface. So I invite you at this moment to kind of scan down the table, see if you can list your own half-cell reactions that would indicate how copper would participate, taking copper 0, copper solid, to an ion form, generating electrons that could be used to reduce zinc. See if you can predict what those half-cell reactions would be and what the outcome for the overall cell would be. As we saw above, we had 0 volts as the sum there. So try to determine your sum for the cell potential here. Okay, so maybe you obviously listed that we need to still work with those same zinc ions above. So we're trying to get zinc 2 plus aqueous plus 2 electrons to still form zinc solid. That's what the gray matter is. Perhaps there's more driving force involving the copper. So we would consider the copper 0 as a potential source for potential to drive this process. So copper 0 is going to be oxidized to a copper ion form. So as we scan down here in our list, we see a copper half-cell reaction here. Copper can form copper 2 plus ions that would disperse into the media, and we would generate some electrons that way. So we can list our standard potentials for these two half-cell reactions and ultimately the sum of them to see if this is favorable for a spontaneous process. Okay, so again, the zinc ion one is similar to above, so that's our 0.763 volts. As we've seen, we've been trying to get positive outcomes here, so the value in here must exceed 0.763 volts in a positive value to try to overcome the sort of voltage deficit that we have by dealing with zinc ions. So we look at copper, and copper is going to be 0.34 negative. And so clearly that's not going to give us a positive outcome, okay? So that isn't the driving force for getting zinc to be applied to the structure of a penny or a copper plate. Further, as the equation indicates, if that were the case, we would see copper ion dispersing into the solution. And those of you who are familiar with other labs or other experiences with copper tends to apply quite a bit of color to solution when that happens. Typically blues and greens develop, and we did not observe that in this reaction. Okay. So we'll just clean up our notes here to formalize this in our slide. Okay, so no oxidation can be generated there. And sorry, I'm just catching something here that we need to correct, so that was a negative sign there. Okay, and we mentioned the observation that it didn't occur, so that is not what's going on. Okay, so clearly there's more to the story than our initial animation listed there. So the first thing to consider is that the zinc ions presented in this animation have more detail to them. So we're working with high pH sodium hydroxide media, NaOH aqueous is the media. Under this condition, the sort of reductive potential of zinc, the granular zinc in here, can actually provide a stronger driving force for reduction. So notice here in our first step that we're listing that granular zinc, zinc solid, will react with the hydroxide that is in the media and form this zinc hydroxide, zincate it's called, and liberate those same 2 electrons. So the simple view of zinc forming only zinc 2 plus ion hydrated by the water is not fully correct. Hydroxide plays a role here, and as a consequence, the standard reduction potential is modified. So we have a larger value, therefore. Okay, so to put this in context, if we look at our table again, what we see here is that this process of forming zincate gives a little bit more reductive power to the zinc. Zinc was formerly here, as far as reducing species, the strongest reducing species are over here, things like aluminum, sodium, potassium, very reducing. Zinc is in that category, but when we work under high pH hydroxide conditions, we get extra sort of voltage for the process. Okay, so here 1.36, that makes the zinc almost as reductive as aluminum in standard conditions, such as neutral pH, room temperature, and atmospheric pressure. So that's one additional detail. That's so reductive that it'll react with water from that media and liberate hydrogen. So just simply taking zinc and exposing it to high pH sodium hydroxide in water, we will generate zincate ions and gas, hydrogen gas, at the expense of some water and some of the hydroxides from that sodium hydroxide. Okay, so the net process here gives us an E cell that is positive, and our delta G equals minus NF E cell ends up negative, and this would be a spontaneous process. So we expect granular zinc to form zincate in sodium hydroxide aqueous spontaneously. Okay, and not only that, as zinc is forming zincate ions, so I'll put quotes on these ions now, that we have a stronger driving force, almost as strong as aluminum under standard conditions there. Okay, so this is a key new detail for us to understand how this happens. The second detail here is to consider more about where the zinc is going. Okay, so we see here that zinc ultimately develops across the surface in the animation, and at a simple view is that, we're simply adding a layer of zinc external to the copper. But the additional detail here is that the zinc actually is known to rapidly alloy with the copper to form brass. So if you haven't looked at brass before, it's a substitutional solid solution of the two metals. So what we have is zinc can take any place of the copper atom in the body-centered cubic lattice of crystalline copper, and vice versa. And the pattern of the minor atom in the host material is random, so we call that a solid solution. These are in fact solids at room temperature, but the randomness speaks to a solution state. And so this the outcome here. Here you see in one representation we've put the zinc at the center of the body center cubic lattice, but statistically it's equally likely to position that zinc at any other spot in that lattice. Brass typically has proportions by atom percent between 5 and 40 atom percent. And this allows one to create a whole range of materials with different properties. What we also know is that zinc readily diffuses into copper even at room temperature or under the conditions of the heated sodium hydroxide media that we saw in our video and in this lab. What this translates to is a very low activation energy in the calculation for the diffusion constant at these sort of non-standard conditions. So because the activation energy is low for getting zinc to diffuse, the overall diffusion constant is low, and this will readily happen even at room temperature. Some of the properties of the resulting brass. We can have brass that's more malleable than zinc itself. Zinc is quite brittle, and the overall resulting brass has composition-dependent properties such as melt point and hardness. So the ability to tune the range of zinc in a brass can be advantageous for dialing in the right properties in a material. And folks have taken advantage of that to access, very robust, corrosion-resistant metals and therefore alloys, which has applications on external in-service applications like doorknobs out in the environment, locks, for example, or even musical instruments where the sort of tone of the sound can be tuned by the amount of zinc in the copper alloy. So lots of different interesting details here on brass. Key takeaways for us are the idea that zinc can readily diffuse into copper even at room temperature. And so what this does to help us better understand what's happening in this part of the lab is that we don't simply have a separate plane of zinc developing across the surface, but rather an alloy forming as we observe that kind of gray. So it's going to be kind of a very zinc-rich alloy that is forming with time, and that is what is observed in the final gray pennies or the gray copper sheets that you might see in your lab. Okay, so to put that in context, here from a nice article from the 90s, we have the idea that this reaction occurs due to electrochemical potential differences, like we've been seeing, considering the E naughts, for example, considering the different forms of zinc. Okay, so we've already considered zincate ions and an additional sort of reductive power that way. So not just simply the ion of zinc 2+. And the driving force of the reaction is a brass alloy forming at the surface of the copper as we go. So to help us understand the implications here, we also learned a moment ago that brass can have a lot of range. So alpha brass is typically a brass that has a content that's a bit less than 35 atom percent in zinc content. Gamma brass is more zinc rich, so the zinc content is more than 45 atom percent in that regard. What the authors here of this paper have done for us have done some measurements on the kind of potential of the cell that is created as we execute this step. So getting granular zinc to plate out zinc onto a copper structure. So initially working with those zincate ions to form zinc in a phase of copper. So that is the indication here of the subscript Cu forming zinc in copper. So that's the terminology for alloy formation at brass. The initial voltage here of the whole cell is about 1 volt. And this is where we have very low zinc content brass at the surface, or almost none at all even. Okay, so very high voltage driving force, high spontaneity expected here by the delta G equals minus NFE equation when there's very low zinc content in the copper. With ongoing deposition of zinc into the copper as an alloy, the alloy is becoming enriched in zinc at the surface, and diffusion isn't effective enough to bring all of that zinc into the coin or into the copper structure, and we see a gray developing indicating enriching of the surface in zinc, but still in the form of an alloy. What happens is the overall cell potential drops. So we start at around 1 volt when we have very little zinc, and it starts to drop towards 0 for the overall sum. Okay, so the net result there is that we start losing the driving force for having a positive, high and positive E cell value here. Okay, so this is dropping with time, and we are losing our driving force to have negative delta G values. So that is to say that this plating mechanism is limited by the amount of zinc that is applied to the process. Okay, so in that regard, until all the zinc is kind of infused deeper into the copper, the process will sort of self-regulate and stop. Okay, so considerations there in this paper that were taken to come to these conclusions are listed here. They considered taking granular zinc in zinc as a medium to make these alloys. We considered zinc and copper for our lab, but they've considered zinc into platinum, into silver, into graphite, into iron, and even into cadmium. And they found that the driving force, the E cell values, were responding and decreasing. Okay, so here asking zinc to establish alloy or an intermetallic with different metals impacts the overall E cell value and therefore the spontaneity. They found that they actually couldn't even get zinc onto cadmium because the overall driving force was from the outset too low. So they didn't even have a high initial starting point there like we had described a moment ago. So it was this idea that the brass and how zinc rich it is what limits this deposition process. Okay, so to put that into further context here for us, we'll just look at the half cell reactions for this alloy forming step. Okay, so here we are. This is the reaction for us in question. Granular zinc liberating 2 electrons into the copper, creating zincate ions into solution. We're going to need a half cell reaction for that. And then zincate ions into solution, providing zinc 0 atoms to alloy into the copper structure. And the 2 relevant half cell reactions are here. We saw this one a moment ago when we discussed and introduced the zincate. So granular zinc in a phase of zinc, reacting with the hydroxide to form zincate ions, shown here, and liberating 2 electrons into the conducting metal copper. Those 2 electrons being used to react with zincate ions from solution, and now as a driving force making a different zinc than what we started with, making an alloy zinc. And here you can see that the overall impact on the total E of the cell, potential of the cell, is modest because we have a driving force given from the entropy by diffusing copper into the zinc. And that brings us a lower value here for this half cell reaction. Okay, so in by this regards, we know that we're going to be strongly positive here and expect a very negative delta G value as an outcome there. Okay, so those are the kind of half-cell electrochemical considerations to describe what's going on in this seemingly simple experiment. Okay, so yeah, we mentioned it a moment ago that the idea of working with zincate rather than simply neutral pH zinc ions is an important detail here. Get a little bit of extra reductive power reflected over here to help us maintain positive E values for overall spontaneity. Okay. So yeah, again, to emphasize it further, it's the formation of this alloy at low temperature that is the driving force that is important here. Trying to minimize this negative value to not drive our overall E cell into a negative territory to negate any spontaneity. So that is how we justify the ultimate kind of ideas of forming the gray penny. The gray we see is not a kind of an independent layer. It's worth to kind of consider that just temporarily, if you will, if you want to apply some methods like Fick's second law for diffusion. But ultimately, to kind of accelerate the diffusion of the zinc-rich brass at the top, gamma brass, to be more of an alpha brass, we need to apply heat. And so that's what we see the role of the hot plate, helping us get zinc atoms to swap with copper atoms and diffuse zinc in the gamma brass layer deeper into the copper and make a more yellow brass that is less zinc rich. Okay, so in a sense, after time, even in the gray brass, we have a diffusion result, and the sort of zinc-rich brass that one would have will definitely be transformed into a low zinc brass, labeled as alpha brass here, with more time, or with short time but on a hot plate. Okay, so those are the additional details of a very simple kind of observation and very kind of fun lab for forming brass for working with granular zinc in sodium hydroxide. So for our lab, we're going to take a lot of notes on the solution reaction that we have to deposit zinc on copper. We'll be working with a copper slab rather than pennies. We'll look at the annealing, so the heating of those kind of gray copper slabs. We'll be monitoring that annealing carefully to make sure that there's no oxidation. There's a bit of a competition between getting that structure to heat and therefore transform the gray brass, gamma brass, into an alpha brass, and not overheating and triggering oxidation of the metals or the alloys. The samples will then be characterized. So we'll have 3 samples. We'll have a pristine copper slab characterized. We'll have the zinc plated copper. So this is the one that is we now understand to be very zinc rich. So a zinc rich brass there. And then the one that is produced after by heating on a hot plate to diffuse that zinc-rich brass into more zinc-deficient brass. Okay, so we'll look at that by simple observations with one's eye. So in our videos, for example, we'll look for color changes. We use optical microscopy to look at the surface grain structure to see if anything has changed there. We'll use SCM microscopy to look very close under high mag conditions and even at a cross-section to see if we can understand just how thick or thin these brass layers are. And then we'll compare elemental composition and of the surface and in the cross-section using energy dispersive X-ray spectroscopy to see if we can justify what has happened here to transform the copper slab into a brass. Okay, so some important considerations here for us are to consider analysis depth of the characterization techniques. Okay, so consider analysis depth of the characterization technique. And what implication that might have on the overall averaging of signal from very topmost layers in the surface to deeper in the copper, and to see if that might justify some of the changes in the resulting data. And lastly, we'll also look at the XRD to see if the crystal structure of the surface is transformed as we take these copper slabs from their pristine initial state to a zinc-rich brass, and then ultimately to a more zinc-deficient brass. Okay, so we'll ask questions like, does the XRD spectra match that of pure copper, pure zinc, or is it a spectra that's distinct from the two in the form of an alloy? Try to observe some differences there in the spectrum. Okay, so that is part 2 for this kind of corrosion type lab, looking at brass as a role there for